Welcome to KubeCon North America. My name is Tushar Gohar. I am one of the principal software architects at Intel. My focus here is on storage software. My colleagues Joseph and Tim will join me for the later part of this presentation to walk you through this Intel MinIO joint demo, showcasing our joint work on cloud-native frameworks and object storage workload acceleration. So let me set the stage here. Today, we'll be discussing our contributions to accelerate cloud-native object storage, specifically within the context of MinIO S3 object storage, in the context of a Kubernetes cluster that utilizes Intel's optimized software libraries. In the second part of the demo, Joseph will describe how to bring up a Kubernetes cluster with MinIO as the object storage provider using Intel bare metal reference architecture, also known as BMRA. BMRA automates complex steps involved in a cloud-native or even an edge-native cluster setup and makes it easy for customers to test run and consume their applications. And finally, Tim will show a demo section that will be hands-on, more of the hands-on section of the demo that will demonstrate how your cloud-native environment can be customized to easily achieve higher performance with MinIO running on Intel Xeon scalable platforms. So for some background on object storage, let's talk about the choice of primary storage. In the public cloud, object storage is almost always primary storage. In other words, object storage has become synonymous with the cloud-native operating model when it comes to storage. Now, it is not just a random choice. Performance, scalability, cost, as well as reliability, durability, and security have also been proven superior in object storage. Cloud providers have ensured that object storage is superior in terms of pricing as well by pricing their file and block tiers much higher, rather, than the cost of object storage. Talking about MinIO as the specific object storage instantiation, it offers a high-performance S3 compatible object storage, which is designed to be native to Kubernetes. And in fact, it is the only object storage suite available that has support on every public cloud, including the AWS, Azure, and GCPs of the world. Every Kubernetes distribution, and it applies to applications running on private cloud or even the edge. MinIO is software defined and is 100% open source, licensed under the GNU AGPL version 3 license. So let's talk about a few additional things that make MinIO attractive. MinIO strives at doing one thing and one thing well, that is object storage, which allows MinIO to put a lot more focus on performance of object storage. It's designed with simplicity in mind. Core parts of MinIO are written with hand-coded assembly. So they are able to utilize SIMD instruction sets such as AVX512, which are found on commodity processors, including the Intel Xeon scalable processors that allow MinIO to deliver the best performance that Intel processors bring to bear. Now, being fast allows MinIO to expand the map when it comes to workloads. It can be used as primary storage in the cloud, but then specifically also for workloads like analytics, AI/ML pipelines, and cloud and edge application workloads. So in a sense, this allows MinIO to be not just archival storage, which object storage has traditionally been known for. And it's no surprise that MinIO is one of the fastest growing open source storage communities out there. In fact, talking about statistics, it has exceeded over 1 billion Docker pulls to date. Why does Intel matter for MinIO's high-performance S3 compatible object storage. Intel's trusted platforms feature crypto accelerators that securely boost data transfers, and in particular, the use of AVX512, AES-NI, or SHA-NI as part of the native instruction set available on the Intel's Xeon scalable processors. MinIO is written in Golang, and it uses a number of foundational Golang libraries for crypto hashing, erasure coding, etc. The MinIO team has been collaborating very closely with the Golang and storage-focused software teams at Intel to optimize these foundational Go libraries. As a result, MinIO has been able to leverage enhancements to the performance of erasure coding, as well as TLS for on-the-wire encryption. And as we will demonstrate in this session, enhancements to the performance of hashing primitives as well. So in the later part of this presentation, Tim will showcase these hashing improvements that are key to accelerating object placement function, which is part of almost every put or a write operation that MinIO performs. So with that, I will hand it over to Joseph to describe how to leverage the Intel bare metal reference architecture, which is designed to shorten the paths to day zero deployment of cloud-native solutions.
In order to deploy the full stack of the demo, similarly to deploying any other performant workload, there are several technical details that need to be considered. Example of these parameters can be kernel boot configuration parameters, creation of huge pages, several configurations related to the network interfaces, NUMA-related configurations which reflect how the platform memory gets organized with respect to software locality, etc. Also, other software such drivers and platform-optimized libraries need to be installed and configured in order to help the workload run efficiently. If all these installations and configurations are done manually, there is always room for human error. That will require extra cycles of debugging through the whole stack, which is a pretty tedious task that can become a sinkhole for the organization. Also, knowledge of all these details is not abundant, and some engineers consider it a black art. For these reasons, Intel is developing the reference architecture, Array, to allow deploying all the above in an easy way. Intel provides a set of configuration profiles, which is a list of software components and configurations in YAML format, with some code that will invoke Ansible behind the scenes and deploy everything on a host or a cluster with ease and minimizing room for human errors. The user can deploy these profiles into bare metal servers, BMRA, into virtual machines, VMRA, and now on public cloud, Cloud Array. As an extension, Kubernetes can also be deployed, allowing a full deployment for your workloads. Finally, when the user is intimate with the configuration profiles and know what they're doing, they can create or modify their own profiles. But now, let's get back to the MinIO demo. During this portion of the presentation, we will be performing a live demo of the improvements to MinIO TLS performance during GET operations. In this case, depending on the object size, we observe up to a 10% performance improvement in terms of achievable GET throughput when performing TLS operations with AES GCM enhancements available with the VAS instruction set provided with the third-generation Intel Xeon scalable processors.
Hello everyone, my name is Tim Miskell, a cloud software architect, part of the Customer and Ecosystem Enabling Division at Intel. And today we will be presenting a live demo of some of the crypto optimizations from MinIO that leverage the SHA-NI instruction set available from third-generation Intel Xeon scalable processors. In terms of the deployment model for the demonstration, we deploy MinIO using the bare metal reference architecture. Each of the MinIO pods are deployed onto a distinct controller node. We format each of the NVMe drives with a 4 kilobyte sector size and afterwards we XFS format the corresponding drive. We create a pool of PVs for each MinIO node, and we also create a pool of VFs using the SRV network operator. We configure the MTU for each VF to 4 kilobytes, and we created a separate DHCP network for the storage plane. Afterwards, each of the MinIO antenna pods are deployed into a set of 4 storage nodes. As mentioned, with 3rd generation Intel Xeon scalable processors, we have access to the SHA-and-I instruction set, which can be used, for example, to accelerate SHA-256 hash operations. As part of this demo, we leverage a set of updates to the Golang libraries that leverage the underlying SHA-and-I ISA. In turn, our MinIO antenna pods directly benefit from this enhancement as they are built on top of these updated Golang libraries. This slide presents an overview of the hardware and software BOM for 1 out of the 4 of the MinIO storage nodes, noting that all 4 of the storage nodes are identical in terms of hardware and software. In this case, each of the MinIO storage nodes is populated with 8 NVMe drives, each with a capacity of 4 terabytes, for a total of 32 drives, along with 128 terabytes of capacity. As mentioned, each node also has a separate dedicated interface for handling network traffic over the storage plane. At this point, we present a 2-part demo. For the first part, we demonstrate the put throughput performance for a baseline MinIO antenna pod. That is, a MinIO antenna pod that does not include the updates to the Golang libraries delivers the underlying SHA-and-I instruction set. In this case, we connect to the MinIO antenna pod using a benchmarking tool referred to as Warp. In this case, the Warp client performs a series of put operations against the MinIO antenna pod using a 64 megabyte object size for a duration of 2 minutes. Once the 2-minute duration completes, it will display the baseline put throughput performance number. As before, we deploy a MinIO antenna cluster using the BM array tools. The baseline test is completed, and at this point, we have an average put throughput of approximately 1500 megabytes per second. For the second part, we demonstrate the put throughput performance of MinIO antenna pod rebuilt with the updated Golang libraries that leverage the underlying SHA-and-I ISA. As before, we use the Warp client tool to perform a series of put operations against the updated MinIO antenna pod using a 64 megabyte object size for a duration of 2 minutes. At the completion of the 2-minute benchmark, we compared the put throughput performance against the baseline. In this case, we observe up to a 50% improvement in put throughput performance, not only for a single MinIO storage node, but also at a cluster level, in this case with a 4-node MinIO storage cluster. In this case, the second part of the demonstration is completed. In this case, we're able to reach a put throughput performance of approximately 2300 megabytes per second, and if we do the math, we're able to achieve just over 50% performance improvement. The following slide presents our recently published results for MinIO Object-Storage performance with 3rd generation Intel Xeon scalable processors. In this case, given the support of PCIe Gen 4 on the platform for both storage and network devices, along with the increased core count, we're able to achieve up to a 1.8x improvement in put throughput performance, along with up to a 2.3x improvement in get throughput performance when compared with the previous generation of Intel Xeon scalable processors. The following slide presents the results from today's live demo, both for a single node as well as a multi-node MinIO storage cluster for a variety of core count allocations. In this case, with the new SHA-and-I ISA available from 3rd generation Intel Xeon scalable processors, we're able to achieve up to a 48.6% put-through performance improvement versus the baseline, in which case we do not leverage the underlying SHA-and-I ISA. In terms of getting the most out of MinIO Object-Storage, please be sure to connect with MinIO directly over Slack or consider contributing to the MinIO project. In terms of trying the performance improvements highlighted today, the Golang patches have been upstreamed and are available to try on your own MinIO Object Store. Please feel free to review the improvements to both SHA-and-I, along with AHGCM with AVX-12 support. And in terms of the BMRA reference architecture, please also be sure to visit Intel Network Builders for more information, as well as the following GitHub repository to try it out for yourself. This concludes today's presentation. Thank you so much for your time today.